Welcome to Mechanical Engineering at University, Sains, Malaysia. Explore computational fluid dynamics. Our faculty brings research and expertise. First, Associate Professor Yuko Hua. He specializes in microfluidics and heat transfer for electronics, pushing thermal management. Next, IR Dr. Ahmad Fikri Mustaf, expert in fluid dynamics and turbomachinery. His work optimizes fluid flow and energy conversion in machinery, crucial for innovation. Finally, Associate Professor T.S. Mohammed Sharizal Abdul Aziz, innovator in CFD, FSI, and AI-assisted engineering. Join us to learn from these experts and shape engineering's future.
Welcome to our Microcredential on Product Failure Analysis in Semiconductor, focusing on computational fluid dynamics. This program builds a semiconductor-centric CFD pathway, guiding you from fundamental principles to decision-ready modeling. You'll start by understanding CFD's role in packaging failure analysis, core governing equations, flow regimes, and microelectronics heat transfer essentials. The curriculum then moves through the standard CFD workflow: geometry, meshing, physics setup, solution, and post-processing. These skills are applied to advanced packaging cases, including CU stacks, molded underfill, microchannels, and fin arrays. The capstone project involves an end-to-end conjugate heat transfer setup for a chip, heatsink, in an air enclosure. This emphasizes simple, defensible model choices, basic convergence checks, and clear reporting using decision metrics like junction temperature and pressure drop. Upon completion, you will have semiconductor-focused CFD foundations, covering failure context, governing equations, and heat transfer essentials. You'll also gain practical CFD setup and application skills, including meshing strategies, advanced packaging use cases, and decision-ready post-processing. Module 1 introduces CFD as a fast, cost-effective way to analyze thermofluid behavior in semiconductor devices. It replaces hard-to-instrument experiments with numerical solutions of continuity, Navier, Stokes, and energy equations. Learners review common modeling assumptions and see how CFD reveals hotspots, heat flux paths, and airflow resistance. The module surveys package-relevant failure modes like underfill delamination, solder fatigue, and die cracking. It links these to appropriate flow and heat transfer regimes, from conduction-dominated microgaps to laminar/turbulent external cooling. By the end, you can articulate why and where CFD adds value in advanced packaging. Module 2 grounds learners in the heat transfer physics that drive thermal behavior in semiconductor devices and packages. It clarifies heat versus temperature and quantifies heat via conduction, convection, and radiation. These principles are applied to the typical die, TIM, spreader, heatsink, air path, and microelectronics. Learners use core dimensionless numbers, Reynolds, Prandtl, Biot, and Grashof, to reason about regime selection. Module 3 introduces the CFD purpose and end-to-end workflow, from geometry to post-processing. This includes meshing with boundary layer inflation, physics and boundary condition setup, and solving with basic turbulence models. You'll learn post-processing techniques like contours, vectors, pressure drop, and mass balance checks. This prepares you to run a simple baseline case and interpret convergence before moving to complex problems. Module 4 turns semiconductor-relevant heat transfer problems into a clean, step-by-step CFD setup. You'll build fluid, solid domains for CHT, apply shared topology, and generate meshes with boundary layer inflation. Then, configure fluent physics, boundary conditions, turbulence, and basic solver settings. Finally, run to convergence and prepare for post-processing of temperature fields and cooling performance. Module 5 connects real semiconductor packaging challenges to practical CFD study design. Learners translate defects and thermal risks, hotspots, molded underfill issues, microchannels, and fin arrays into clear CFD scopes. A lightweight workflow is emphasized. Define the problem, pick basic models, run checks, and communicate findings. Findings are communicated with decision metrics like junction temperature, pressure drop, and thermal resistance. Module 6 guides learners through an end-to-end conjugate heat transfer workflow for a chip and heatsink in an air enclosure. You'll build clean geometry, generate an appropriate mesh, and configure core physics and boundary conditions. Learners practice extracting decision-oriented outputs like temperature contours and total heat transfer rate. The emphasis is on a practical, repeatable setup that communicates assumptions and results effectively. Enroll now to master product failure analysis in semiconductors through advanced computational fluid dynamics.